module, you will learn about the electronic configuration of elements. We can define electronic configuration as the distribution of electrons into various orbitals of an atom. Before we begin to understand the electronic configuration of atoms, let's recap the three main principles that guide the filling of electrons into various orbitals in an atom. First is the Aufbau principle. It states that in the ground state of the atoms, the orbitals are filled in order of their increasing energies. In other words, electrons first occupy the lowest energy orbital and then enter into successive higher energy orbitals. The electrons enter into various orbitals in an increasing order of n plus L value. Second is the Pauli's exclusion principle. It states that an orbital can have maximum 2 electrons and these must have opposite spins. And finally, the Hund's rule of maximum multiplicity that deals with filling of electrons into equal energy orbitals of the same subshell. It states that electron pairing in p, d and f orbitals cannot occur until each orbital of a given subshell contains 1 electron each or is singly occupied. We can represent the electronic configuration in two ways. One way is to represent it by the orbital diagram method. In this method, the orbital is represented by a box and an electron is represented by an arrow in it. If the spin of the electron is in a clockwise direction, then the head of the arrow points upwards. If the spin is in an anti-clockwise direction, then the head of the arrow points downwards. A clockwise spin is called the positive spin and anti-clockwise spin, it is called the negative spin. The other way of representing the electronic configuration is by the NLX method. Here, N represents the number of the principal shell, that is 1, 2, 3, etc. L represents any subshell or any orbital. S, P, D, F and X represents the number of electrons present in that orbital. For example, 3p2 denotes that the p subshell of the third principal orbit contains 2 electrons. Now let's discuss the electronic configuration of the first 10 elements: hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Hydrogen has only 1 electron which must be filled in the orbital of lowest energy, that is 1s. Helium has 2 electrons. Both these electrons can be filled into the s orbital. However, according to Pauli's exclusion principle, these 2 electrons should have opposite spins. Lithium has 3 electrons. 2 electrons will fill the s orbital, while the remaining 1 electron goes to the orbital of next higher energy, that is 2s. Beryllium has 4 electrons. 2 electrons fill the 1s orbital, and the remaining 2 fill the 2s orbital. Boron has 5 electrons. The first 2 electrons fill the 1s orbital. The next two fill the 2s orbital. And the fifth electron occupies the 2p orbital. Actually, the fifth electron may occupy any one of the three 2p orbitals: 2px, 2py, or 2pz, because all have the same energy. However, conventionally we always fill 2px, 2py, and 2pz in that order. Carbon has 6 electrons. The first 4 electrons fill the 1s and 2s orbitals. The remaining 2 electrons will go to any 2 of the 3 2p orbitals in accordance with Hund's rule, and these will have parallel spins. Nitrogen has 7 electrons. The first 4 electrons fill the 1s and 2s orbitals. The remaining 3 electrons will go to the 3 2p orbitals in accordance with Hund's rule, and these will have parallel spins. Oxygen has 8 electrons. Fluorine has 9 and neon has 10 electrons. In each of these elements, after filling the first 4 electrons in 1s and 2s orbitals, the remaining electrons enter into next higher orbital, 2p, according to Aufbau principle. They successively occupy the 3 2p orbitals, that is 2px, 2py, 2pz, in accordance with Hund's rule. The pairing of 2p subshell starts with oxygen and completes with neon. The electronic configurations of other elements are written in the same way. After filling the 2p orbitals, the electrons fill the 3s and then the 3p orbitals. We can also write the electronic configurations of most of the elements in a simplified manner or condensed form. For example, the element sodium, that has 11 electrons, has 1 electron more than its nearest noble gas, neon. The 11th electron will enter the 3s orbital. Therefore, the electronic configuration of sodium, which is 1s2, 2s2, 2p6, 3s1, 1s2, 2s2, 2p6, 3s1, can also be written in a condensed form as neon 3s1. Similarly, the electronic configuration of magnesium can be written in a condensed form as neon 3s2. Observe how the electronic configurations of elements with atomic numbers 11 to 17 are written in a condensed form in terms of neon. Argon, whose atomic number is 18, has a completed 3p orbital. Therefore, the electronic configuration of potassium, which has 1 electron more than argon, can be written as argon 4s1, where Ar represents the core of noble element argon. The electronic configurations of the atoms generally follow the 3 above said rules for filling up electrons into various orbitals. For example, in potassium, the electrons enter into various orbitals, that is 1s2, 2s2, 2p6, 3s2, 3p6 and 4s1 in accordance with Aufbau's rule. However, in some cases, the actual configuration differs slightly from the expected ones. The electronic configurations of chromium that has 24 electrons and copper that has 29 electrons do not follow the general trend. The electronic configuration of chromium is expected to be as 1s2, 2s2, 2p6, 3s2, 3p6, 3d4, 4s2 and the electronic configuration of copper is expected to be 1s2, 2s2, 2p6, 3s2, 3p6, 3d9, 4s2. But actually their configurations are 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s1 and 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1 respectively. This happens in certain elements when two subshells differ slightly in their energies. An electron may shift from a subshell of lower energy to a subshell of higher energy. If this shift results in symmetrical distribution of the electrons in the orbitals of the subshell that has higher energy. The anomaly in chromium is attributed to the fact that half-filled orbital 3d5 has lower energy and extra stability. In copper, the completely filled orbital 3d10 has lower energy and extra stability. The two reasons for the extra stability of half-filled and completely filled subshell configuration are the symmetrical distribution and exchange energy. From the expected electronic configuration of chromium, if one of the 4s electrons shift to the vacant 3d orbital, the distribution of the electrons will become more symmetrical and this will impart extra stability. Similarly, in the expected electronic configuration of copper, if one electron from the lower energy 4s orbital is shifted to higher energy 3d orbital, it will make the distribution of electrons symmetrical and hence will impart more stability. Stability also occurs whenever two or more electrons with the same spin are present in the degenerate orbitals of a subshell. These electrons tend to exchange their positions, and the energy released due to this exchange is called exchange energy. The number of exchanges that can take place is maximum when the subshell is either half-filled or completely filled. As a result, the exchange energy and stability are maximum. You have now reached the end of this module. In this module, you have learnt that the three main principles that guide us on the filling of electrons into various orbitals in an atom are the Aufbau principle, Pauli's exclusion principle, and the Hund's rule of maximum multiplicity. Electronic configuration can be defined as the distribution of electrons into various orbitals of an atom. We can represent the electronic configuration of atoms in two ways: orbital diagram method, NLX method. We can also write the electronic configurations of elements whose atomic numbers are between 11 and 17 in terms of the electronic configuration of neon. In some cases, the actual configuration differs slightly from the expected ones. Example, chromium and copper. This is because of the extra stability of half-filled and completely filled subshell configuration. The cause of this extra stability has been attributed to the symmetry distribution and exchange energy.